Hi folks, Dr. K here with today's Science Untangled topic on balancing equations, part 1. With the main question being, how can we efficiently balance equations? Now, for a little bit of background, let's look at what you might use them for. Now, first of all, why should it be balanced? Well, that goes back to conservation of mass. We're supposed to have the same total of reactants as products. So that implies balancing to begin with. Now, building on that, once we have a balanced equation and we have certain amounts of reagents or reactants, then we can say something about which reactant is in excess or is limiting, which can be important for various reasons that we'll get into later. And finally, you can take it one step farther, and once you've got a balanced equation, you can start doing calculations for energy. How much energy is given off per mole of one reactant or another? How much energy is given off per mole of something produced? Okay, so let's take a look at a few examples. We'll start with the more straightforward ones, and then in part 2, we'll go into some more challenging ones. But let's start with the foundation, as I talked about in an earlier clip. So looking at something like just your ordinary squeaky pop reaction, where we have hydrogen reacting with oxygen to form water. Now, I haven't even worried about states here so far. Let's just assume that they're all in the gas phase. Although if you do the squeaky pop reaction, you will see the water condensing on the inside of your test tube quite rapidly. Now, with this one, we can easily see that we have two hydrogen on the left and on the right, so seemingly that's okay. But right now we have two oxygens here and we only have one here. So to fix that, of course, we just put a 2 in front of the water. Now we have two oxygens on the right, but now we have four hydrogens, so we put a 2 over here, and that's balanced. Done. While balancing equations, especially for exam conditions, I would normally put in the 1 over here for the oxygen, for the simple reason that way you show that you've considered it. Okay? Normally for a chemical equation, you don't have to worry. If it's a 1, you can leave it out. Moving on. So here we have the combustion of methane, so the reaction of methane with oxygen, right? Methane and oxygen in the gas phase, carbon dioxide gas phase, water presumed in the gas phase due to the energy given off. Okay, now if I start with 1 methane, then I should end up with 1 carbon dioxide, right? Because if we look at the elements involved, and I just look at this, let's restart this, and we just look at this from the point of view of what do we have to start with. We have 1 carbon on the left, we have 1 carbon on the right, we have 4 hydrogens on the left, and we start off with 2 on the right, and we have 2 oxygens and 3, so not really balanced. Carbon's fine, so for now let's go back to that 1 and that 1, no problem. But that means that my hydrogen needs to end up being a 4 on the product side. We can do that, and then that becomes a 4. Okay, so carbon and hydrogen balanced. Lastly, oxygen. With the change to water on the right, I now have 2 oxygens from the carbon dioxide, and I also have 2 oxygens from the water. So we need a 2 in front of the O2. So this had already become a 4, and now this is a 4 as well, and it's balanced. Okay? Can you figure this one out without going through the trouble of actually writing all this down, yes, of course you can. So still doable with this. But I wanted to show you what a very solid way is of working out the details if you can't see it right away. Okay, moving on. And this is one of those that for some people is very straightforward. They can see right away what's going on with it. And other people get confused because there are too many letters in there. And it happens. So we can go left to right. So if I have potassium and iodine, and I have my lead, and now I am not going to write down my nitrogen and oxygen separately here. There is no need, because the nitrogen and the oxygen stay together. We have nitrate on the left and we have nitrate on the right. So I can treat that as one unit. Okay? Now, the lead nitrate here is the tricky bit. So what I would normally do is look at the most complicated looking thing first. So if I look at lead nitrate and we start off with a 1 over here. Wait. Going a touch too fast here. First off, let's go back. We have 1 potassium on the left. We have 1 iodide on the left. We have 1 lead. And we have 2 nitrates. On the right, we have 1, we have 2, 1, and 1. So that's a starting point. Sorry, forgot that. Now, going back to what I said about the most difficult thing. The most difficult looking thing tends to have the lowest number in front of it. Tends to. Always exceptions. So let's assume that we have 1 of these. Yeah? So that means that on the right we also must have 1 lead. So that means we get a 1 here. Okay, so the lead is balanced. It already was, so great. But the nitrate also needs to be balanced, so that would imply that we have a 2 in front of the potassium nitrate. Great, so this becomes a 2. But then between the 2 iodines here and between the 2 nitrates here, that's all fine. Looking at the potassium though, we must have a 2 over here as well. And now, if I work this one out, this becomes a 2, this becomes a 2, and the iodine also becomes a 2, and now we're balanced. Okay, one more. This one throws in an extra little problem, in that mathematically it becomes a little bit more interesting. There we go, that's better. So if I treat this the same way as I did the methane combustion, let's assume we start off with 1 of these. If we start off with 1 of these, we must have 2 here, right? Because the carbons need to balance. If we have 1 ethane, 1 C2H6, right? Then that's 6 hydrogens. So that would make 3 H2O. So far, so good. Nice and easy. Now, if I add up all my oxygens, I have 4 from the carbon dioxide, and I have 3 from the water. So that's 7 oxygens together. That's 3.5 O2. That doesn't work because we always look for the lowest whole number ratio. However, mathematically, this will be 3.5, right? Okay, so what do we do then to fix the rest of it? In this case, because we have a half, we just multiply everything by 2 and job done. So my 1 here becomes a 2, the 3.5 becomes a 7, the 2 becomes a 4, and finally the 3 becomes a 6. And now it's balanced. Okay? It is not an issue if you end up with fractions or decimals during your balancing. okay? As long as you fix it for the final answer. Yeah. And in some cases, when you're calculating energies and such, you may indeed end up with 3.5 because you're asked to calculate the energy given off per 1 mole of ethane, for instance. Okay. So, balancing, the first step done. So, that's it for this one. We will look at some more challenging ones in part 2. Just as importantly, if you like what I'm doing here, please like and subscribe, and leave a comment in the in the comments to let me know what you think and what else you'd like to cover. Okay. Now, based on what we've covered so far, how would you approach balancing more complicated equations? Can you simply look at them and see this goes there, this goes there, this goes there, and we're done? Or do you prefer a more structured approach where you write things out along the lines of what I've been doing here? Okay. Thank you very much. That's it for today.